Welcome to Learn Chemistry Together. This video is about hybridized atomic orbital, methane and sp3 hybridization. Apply valence bond theory to the bonds in methane. Recall the electron configuration of carbon. This electron configuration cannot satisfactorily describe the bonding structure of methane, CH4, in which the carbon atom has 4 separate CH bonds, because the electron configuration shows only 2 atomic orbitals capable of forming bonds. Each of these orbitals has 1 unpaired electron. This could be explained with an excited state of carbon, a state in which a 2s electron has been promoted to a higher energy 2p orbital. Now the carbon atom has 4 atomic orbitals capable of forming bonds, but there is yet another problem here. The geometry of the 2s and 3 2p orbitals does not satisfactorily explain the observed 3-dimensional geometry of methane. All bond angles are 109.5 degrees, and the 4 bonds point away from each other in a perfect tetrahedron. This geometry cannot be explained by an excited state of carbon because the s orbital and the 3p orbitals do not occupy a tetrahedral geometry. The p orbitals are separated from each other by only 90 degrees rather than 109.5 degrees. This problem was solved in 1931 by Linus Pauling, who suggested that the electronic configuration of the carbon atom in methane does not necessarily have to be the same as the electronic configuration of a free carbon atom. Specifically, Pauling mathematically averaged, or hybridized, the 2s orbital and the 3 2p orbitals, giving 4 degenerate hybridized atomic orbitals. The hybridization process does not represent a real physical process that the orbitals undergo. Rather, it is a mathematical procedure that is used to arrive at a satisfactory description of the observed bonding. This procedure gives us 4 orbitals that were produced by averaging 1 s orbital and 3 p orbitals, and therefore we refer to these atomic orbitals as sp3, hybridized orbitals. If we use these hybridized atomic orbitals to describe the bonding of methane, we can successfully explain the observed geometry of the bonds. The 4 sp3 hybridized orbitals are equivalent in energy, degenerate, and will therefore position themselves as far apart from each other as possible, achieving a tetrahedral geometry. Also notice that hybridized atomic orbitals are unsymmetrical. That is, hybridized atomic orbitals have a larger front lobe and a smaller back lobe. The larger front lobe enables hybridized atomic orbitals to be more efficient than p orbitals in their ability to form bonds. Using valence bond theory, each of the 4 bonds in methane is represented by the overlap between an sp3 hybridized atomic orbital from the carbon atom and an s orbital from a hydrogen atom. Double bonds and sp2 hybridization. Now, let's consider the structure of a compound bearing a double bond. The simplest example is ethylene. Ethylene exhibits a planar geometry. A satisfactory model for explaining this geometry can be achieved by the mathematical maneuver of hybridizing the s and p orbitals of the carbon atom to obtain hybridized atomic orbitals. In the case, each carbon atom only needs to form bonds with 3 hydrogen atoms. Therefore, each carbon atom only needs 3 hybridized orbitals. We will mathematically average the s orbital with only 2 of the 3 p orbitals. The remaining p orbital will remain unaffected by our mathematical procedure. The result of this mathematical operation is a carbon atom with 1 p orbital and 3 sp2 hybridized orbitals. We can use this hybridization state to explain the bonding structure of ethylene. Each carbon atom in ethylene has 3 sp2 hybridized orbitals available to form sigma bonds with carbon and hydrogen atoms. In addition, each carbon atom has 1 p orbital. These p orbitals actually overlap with each other as well, which is a separate bonding interaction called a pi bond. The p overlap occurs in 2 places, above the plane of the molecule, in red, and below the plane in blue. Nevertheless, these 2 regions of overlap represent only one interaction called a pi bond. To summarize, we have seen that the carbon atoms of ethylene are connected via a sigma bond and a pi bond. The sigma bond results from the overlap of sp2 hybridized atomic orbitals, while the pi bond results from the overlap of p orbitals. These 2 separate bonding interactions, sigma and pi, comprise the double bond of ethylene. Similarly, in acetylene, the sp hybridization of carbon atoms is observed with a linear geometry. Bond strength and bond length. The information we have seen in this section allows us to compare single bonds, double bonds, and triple bonds. A single bond has only one bonding interaction, a sigma bond. A double bond has two bonding interactions, one sigma bond and one pi bond. And a triple bond has three bonding interactions, one sigma bond and two pi bonds. Therefore, it is not surprising that a triple bond, with bond energy 820 kilojoules per mole and bond length 1.20 angstrom, is stronger than a double bond, with bond energy 632 kilojoules per mole and bond length 1.34 angstrom, which in turn is stronger than a single bond, with bond energy 368 kilojoules per mole and bond length 1.54 angstrom. Thank you for watching. Click subscribe for supporting this channel.